All the trick we've looked at so far really is to do with right angle triangles, because angles don't stop at 90 degrees. So the next question then is, all right, well, how do we deal with angles of any size, any magnitude? There's our coordinate plane. We break it up into 4 quadrants. And there you go. Starting in the top right where everything's positive, the first quadrant, going anti-clockwise. That's what I call the butterfly. But in each of the quadrants I've created a right angle triangle that we can use as a reference. The acute angle, it's always going to come back to the acute angle. No matter the size of the angle, we bring it back to an acute one. And that's where we will locate the acute angle. It will always be, the adjacent side will be the x-axis. That's always the case. Now, if this is true, in quadrant 1 everything's normal anyway because we're going from 0 to 90 degrees, so that's fine. In quadrant 2 then, the actual size of the angle will be 180 minus the acute angle. But the sign will change depending. If you look at the x and the y coordinates and when they're positive and negative. Now the hypotenuse, we always assume is positive because we're talking about the length of the hypotenuse. So sine opposite, well that's still going to be positive because it's a positive y value over the hypotenuse, so sine is positive. However, when we get to cosine, the adjacent side is now negative. So it'll be negative over positive, we end up with a negative, and tan is the other way around, positive over negative, but it still is a negative. In the third quadrant, it becomes 180 plus the acute angle. But again, if we look at that right angle triangle, we see now sine becomes negative, cosine is still negative, and the tan ratio becomes positive. And our final quadrant, which would be 360 degrees minus the acute angle, sine is negative, cosine now becomes a positive, and tan is a negative. Now, using that, we can find things like this. If we bring it back, always bring it back to the acute angle. Now, I know you've got calculators and you can press the buttons and bingo, the answer comes up. But it still is important to know where it comes from, because if we're dealing with algebra or something like that, we can't just plug it into a calculator and get an answer. So 260 degrees, well 260 is in the third quadrant. So we're saying 180 plus what is the acute angle? Well, that would be 80 degrees. And in the third quadrant, it is negative. So it should give me the same as negative sine 80. Tan 220. 220 is also in the third quadrant. But tan's positive there. The acute angle would be 40 degrees. So we get the same as tan 40. Sec of 105. Now, a couple of things we've got to think about. 105, second quadrant. Secant is the reciprocal of cosine. So in the second quadrant, cosine's negative. The acute angle would be 180 minus what? Well, 75. So it should give me the same as minus the secant of 75, which is minus 3.8637. 430. Well, once we get bigger than 360, all we do is keep subtracting 360 until we get it into one of those 4 quadrants. Now, in this case, I only have to subtract it once, and it turns out to be in the first quadrant. Same as the cosine of 70. 0.3420. You could have negative angles, and all that means is instead of going around anti-clockwise, we're going around clockwise. So if I go around clockwise 67 degrees, well, it's the same as going anti-clockwise 293 degrees. Fourth quadrant, so tan is negative. No big surprise, the acute angle ends up being 67 degrees. Remember, odd function. I could have done that straight away when you think about it. Tan of negative x is equal to the negative tan of x, minus 2.3559. Here's a quick little question. We've got to find the coordinates of P. We know it's sitting on a circle, radius 5, and that angle is 30 degrees. Well, I could draw up that right angle triangle and just work it out. X over 5 is cos 30, so there's the x coordinate. Mind you, cos 30 is an exact value, so we can work that out, 5 root 3 on 2. And y on 5 is the sine of 30, so 5 on 2. So there's my coordinates. What about the boundary values though? We talked about what happens when they're in the quadrants. Well, what happens if they're on the boundary of 2 quadrants? How do we deal with that? So 0, 90, 180, 270 and so on. Well, I draw up a fictitious triangle. The angle down the bottom there is 0 degrees. So we know the angle sum of a triangle is 180. So therefore the angle at the top must be 90 degrees. So there's my triangle. I'm going to say the base is 1. But think about it. If that base is 1 and there's 0 degrees between the hypotenuse and the adjacent, that means that the opposite side must be 0. And then a bit of Pythagoras, well, we know the hypotenuse is also 1. I can now read off the boundary values. So 0, well, sine of 0 is 0, cos of 0 would be 1, tan of 0 would be 0. 90, again, reading off the triangle. Sine of 90 is 1, cos of 90 is 0, tan of 90, 1 on 0. Undefined. So on our graph, we'd end up with an asymptote. 180, okay, which quadrant are we in? Oh, we're on the boundary. Boundary of the second and the third quadrant. So what does that mean for ours? Well, sine, it's positive in the second quadrant and it's negative in the third quadrant. Therefore, there's only one logical thing it could be, and that is 0. Because the only way you can jump from positive to negative is to go through 0. Sine of 180. Cos of 180. Well, it's negative in the second quadrant, negative in the third quadrant, so I know it's going to be negative. Pick whichever quadrant you like, it doesn't matter. Let's say it's the second quadrant. And we said it was 180 minus the acute angle. Well, 180 minus 180 would be 0, so it'd be the same as cos of 0, but it's negative. So negative 1 is the answer. Tan of 180, negative in the second quadrant, positive in the third quadrant, got to be 0. Then we can do a similar thing with 270. It goes between the third and the fourth quadrant. And we end up with negative 1, 0, and negative undefined. Well, there is no such thing as negative undefined. It's just undefined. Of course, you do have a calculator, and you could just print sine 0, and oh, look, it's 0. And the tan one, you would go tan 90. Oh, error. That would mean it's undefined. So let's draw up our graphs then. The boundary values are the key when drawing trig graphs. Pretty much just plot those. So I'm going to draw in the sine one to start off with. I know the sine graph goes between -1 and 1. So I'll plot those on the y-axis. I will mark off each of the boundary values. So every 90 degrees. I've only labelled every second one, but they're marked off every 90 degrees. And I've got a few backwards as well. So the first question I always ask is, where does it start? Sine of 0 is 0, so we start at the origin. And then we said the next boundary value was 1. So I plot 1. And now the pattern is there, because I know I've got to go up and down, up and down. So I go like so. And then we just have to draw a nice smooth curve in between them, and there's y equals sine x. Notice I did not put arrows on the end of the sine curve. You do not put arrows on the end, because an arrow on a graph indicates this continues in the same direction forever. And of course the sine graph does not do that. So we just stop it. We don't draw an arrow. Domain, we can read off our graph, is all real x. Range, in between -1 and 1. There's a thing with trig graphs, they are what are called periodic graphs. Period is just how often does it repeat. And when you're talking about a trig graph, you say, when is it back in the same location? You've got to be careful when you do that, because not only has it got to be in the same location, you've also got to be heading in the same direction. So if I pick, for instance, the origin, I'm at 0. Yes, I'm at 0 again at 180, but I'm not going in the same direction. I'm going down at that point. At 0, I was going up. It's not until I get to 360 that I'm at 0 and I'm going back up again. So it's got to be the same point, but in the same direction. 360 degrees. All right. What else can we tell from this graph? It's an odd function. It has rotational symmetry about the origin. So therefore, anytime I want to work out sine of negative x, I could go minus the sine of x. Cosine. Something interesting happens here. Let me plot all those points in. Cosine starts up there at 1. Then it goes to 0. And then that pattern repeats. Now let's draw it in. Have a look at the two graphs. It's the same graph, except one has been translated. The cosine graph we have translated. By how much have we translated it? How many? Say it again. 90 degrees. Makes sense. They're complementary ratios. So yes, we should see a difference of 90 degrees when we draw it. So there's our cosine curve. Because it is the same curve, but just translated, the domain is all real x. The range is -1 to 1. The period is 360 degrees. Same graph. However, we now do not have an odd function. we have an even function, symmetry in the y-axis. So therefore, if we want to work out the cosine of negative x, that will always be the same as the cosine of x. Well, we can't do sine and cos without doing tan. It'll feel left out. Notice I've not bothered marking any point on the y-axis because this one goes 0 and then undefined. Well, in a graph, when we have undefined in the domain, it's either going to be an asymptote or a point discontinuity. And for a tan graph, it's a vertical asymptote. And then that pattern repeats. X-intercept, asymptote, x-intercept, asymptote, x-intercept, asymptote, x-intercept, back the other way, asymptote, x-intercept, asymptote, x-intercept. Well, we haven't got any points other than that, but we do know curves bend towards the asymptotes. It's got to do that. I also know that in the first quadrant, so between 0 and 90, it's going to be positive. So I know it's up there. Now the negative 90 degrees would be the fourth quadrant. I know tan is negative. So I get something like that. It's very important when you draw this. Don't draw it like a cubic. Right? Your cubic has a horizontal point of inflection. So tangent is flat. Tan x, that slope of the tangent at the origin should be 45 degrees. It's actually the line y equals x. So that's the angle you're trying to get when you draw a tan curve. It's coming through at 45 degrees. That repeats between all of the asymptotes. There's our tan graph in all its glory. So what can we see from that? The domain here is a little bit harder to write. This is the way I write it. Well, it's all real x, except I've got all these discontinuities. Of course, it's impossible to list them all, so I do it using a formula. So x equals 90 is my first one. I know every 180 degrees before and after that, you get another asymptote. So I'm just saying, well, it's plus 180k, where k is some integer. You will always find an asymptote. Range is a bit easier. That's all real y. The period of a tan curve is only 180 degrees, though. It only takes 180 degrees. And now we have an odd function. You've got the rotational symmetry about the origin. So if you want to work out tan negative x, it would be the same as the negative tan of x. What about the reciprocal graphs? I'm not going to do them all, I'll just do one of them. Okay, so let's draw it up. There's our axes. How about I do cosec, which is the reciprocal of sine? So I've just dotted in the sine curve there. Well, we've seen how we draw reciprocal graphs. We said all those x-intercepts will become vertical asymptotes. So let's draw them in. We said 1 was an important point because when you turn 1 upside down, you get 1. So all of those y values of 1 remain the same. What else did we say about reciprocal graphs? If the original graph is increasing, the new graph will be decreasing and vice versa. If it's less than 1, then the new graph should be above 1. So what we end up with is a whole heap of U-shapes between the asymptotes. Okay, they're not parabolas, they're just U-shapes. And that pattern would repeat. As I say, we could do that for the other, the sec and the cotan as well, but that's how we work out what it looks like. Okay, wow, that looks like a lot of work.